chaotic, but yeah, the name has the word chaos, so I have to say chaotic. We'll start with first knowing about what is an attractor. Like, we'll only have a vague idea about what is an attractor. So, as the name suggests, it's something which attracts. Now, suppose you have a system where things are flowing. Suppose water, and there you have a hole, as you have in your bathtub. So, what happens? That water goes into that hole, and there it creates some vortex. Now we can say that thing as an attractor and the whole bathtub as a dynamical system. Now, as you can see, like in a bathtub there is only one hole, but you can have multiple holes in multiple places, and you can see how the water then behaves. So that is what we will see here today, how these things happen. And we won't go to the mathematics more because I also don't know the mathematics. We will go to the coding part, how you can simulate them and how you can make fun out of them. What I'll take next is a multi-scroll attractor. Now this is something that have multiple attractors. So in this thing, in this small matplotlib plot, you can see there are two places here and here. Can you see the cursor?
Yes.
So there is like these two small things where every line is sort of rotating about. How many of you are familiar with the word curled? Okay, seems nice. So for you guys who are not familiar with the word curled.
What?
Curled.
Curled.
Curled. Gradient, divergence and curled.
Gross product of it.
So curled is something that tells, if you have a space, somewhere in the space you can define a curl. That says how much rotational property that point has. That is it. If you have a point from where light is emitting, so there is no curl because every light particle from that point is just emitting. But if you have a vortex for Lorentz system, this is special attractor. Now, this has a name which is of Edward Lorentz's, who in 1963 developed this. He was working on climate predictions, like how climate change happens, how you can define the variables in climates like humidity, wind flow, etc. and plot some differential equations out of that, and you can predict if the climate is now this, what it is going to happen a day after or a year after or somewhere else. So it is, you can see, is a perfect dynamical system. It has a space of our whole atmosphere and it has a time of like 3.6 billion years. So it is a very complicated one. But somehow, I don't know how, he very vaguely approximated it with these three differential equations. These three differential equations are like equations of x, y, z and t. So they are like first order differential equations, but they are sort of connected. And you have this sigma, rho and beta as the parameters. Now this graph that you are seeing here, which is sort of nice, it is very nice. This graph is coming for some particular values of those sigma, rho and beta, which are here, 28, 10 and 8 by 3. Now, our today's goal is to create something like that with, of course, processing. That will do. when he actually found out कि okay, that thing is happening, or that set of differential equations are like very nice, and they are sort of predictive for small climates, sort of like very vaguely. Then this term came up called the butterfly effect. Now, this thing, as you can see, it is like a butterfly. That is the same thing that we saw previously here. But this has this term butterfly. That's it, nothing else. Our goal will be to make a better butterfly than this, with the same things that he used, but just a little bit of tweaking. Because, see, processing is more about art than your scientific jiggles. So we'll focus on the art. Now to start with processing, I want you to see this thing. This thing also showed yesterday. So this is the flow field. This is something let's wait for it to create. Yeah. This is something that starts creating when you have a lot of particles throughout the space, and you have some field value attached to every coordinate. As you can see, that differs, and that's why the particles directed from lower field value to the higher field value, and according to the field value, they'll start making these things. So our attractor is also some sort of similar, where we have the highest field values in our attracting points, where all particles will eventually try to go. This is the understanding we will have of an attractor. Nothing more. A point where everyone wants to go. But no one can stop at that point, because there is nothing physical where it will collide. So the thing happens is very strange. Here you can see these points, these 2 points are our attractors. Specifically these 2 points, where everything is starting to converge. And from every other place, there is also a pretty small attractor, but it is not attracting that much. So its field value is not that high, maybe. This is something that will lead us to understand the attractors more easily. So here in this black screen, there is an attractor at the center. Now where I'll click the mouse cursor, a particle will be created there, and it will get attracted by the attractor. Can you see it? Can you see it now? So the attractor is at the center, and every particle is revolving around it. But it can't go in because there is nothing to collide. So this is the strange system that we are getting here. This is what we will be making today, sort of. This is the Lorentz attractor to another form. I just put it for prettiness, that's it. And this is the Chen attractor. I just put it because they are nice. Yes. Just look at them and appreciate the yeah, they are beautiful. And try to make them obvious. The next thing is R. Wait. Let it start first. Then everything. Yeah. So as you can see, it starts with particles which were rotating in one point. But soon, as they went out that point, they realized, okay, there is another point. Let's rotate about that. And they started rotating like this. That is how they start and do things. I'll be sharing all these projects with you so you can tweak about the parameters. This is the same thing, but you can rotate it yeah, mostly the same thing. This is again another Lorentz attractor which is made by dogs. I don't know to say it. Now let's move to a very beautiful thing. Oh no, not this. Yeah. I don't know what this is, but this looks nice and some attractor business is going on, so I just kept. This I kept so that you can just appreciate what we can do with processing and how fast we can do it. All of this is live rendered and there are like thousands of particles rendering right now, right there in my laptop, and nothing is happening. Okay, these are the points, but there is no attractor in the space. I can put attractors in the space by clicking them. We can see how the points are going. Now there is only one attractor, but I can put another. So some point will come to that. These will help you to try to appreciate how these things work and how chaotic they can be. And how, without knowing the exact analytic solution, only with numerical methods, we can do all these predictions. This is a Mandelbrot set. Nothing more. This thing is a Clifford attractor. Have you heard of Clifford attractor before? Is it? You told Clifford attractor? Okay. Anyway, so I'll repeat it then. This is something that you will find in many physical systems. In many physical systems where you have nonlinear behaviors and you put some dissipative component in the equation, then some system will die out, will go to some value where it will stay. Like if I try to move it will just stop, it just die out. But some systems, there are some who won't, and who will show this random behaviors depending on the conditions, the equations that they follow. This is the main group of equations that they follow, and these are the values. So basically you can see these are the amplitudes and frequencies that govern the attractor. So you can make pretty good one of them. Like there's also some examples of that, so you can try doing it. Oh, they change actually, yeah. But I spent like 10-15 minutes on this and I couldn't figure out how exactly I can control this. So anyway, you figure out. Okay. Now as I am done with showing you the examples, and I tried my best so that you appreciate what we are trying to do. Now we will get our hands dirty and make our attractor. So what we are going to make is something like this. You can move also and rotate a bit. Is it looking like a butterfly? Please respond.
Yes.
Okay. Okay. So yeah, we will make this thing from scratch. Equation. Yeah. So as you can see, these are the equations that we will take, but we have to somehow plot these equations in the processing of program and try to render it somehow so that the particles that follow these equations and they move accordingly. That is what we have to do. Just these equations will make sure we will have attractors and the particle will move as they are attracted by the attractors. So first we will start. Oh, I have to make it bigger. So first we'll create a normal screen there. That is like set up a draw function. Let's see. It's working. Yes, it is working. Yeah. So that is it. Then we have to implement our differential equations. Now how are we going to do it? As you can see, these are like differentiation happening on x. So there is some calculus stuff going on. But we don't care. We work in steps. We have a frame in processing that refreshes, say 30 times a second. So we have to be discrete. And we have to refresh the frame. We will take these as very literal sense. We will take dx as change in x, dt as change in t. Now they will depend on the previous x and y values. That is exactly what we are going to do. So we will take these and put them into the draw function so that they keep updating every time. Let me just pop it from here. Now here you can see, I didn't put dx by dt equal to something. I put dx equal to the value times dt. Because as I said, our campus works in iterations. So we have to progress our system by time. And how much amount of time? That I said as dt. Now more technically in computer science terms, this is called some delta time and they have many sophistications about it. You can do like some frame rate, you can divide frame count by this frame rate and have some time that will be constant. So that's a huge juggle. I won't go into that, I'll keep it as it is. Now this time is just gonna be multiplying with that value that dx has, and this dx value will keep gradually adding up with x along with y and z. So these dx, dy and dz are the increments only, and we will add them with x, y and z. That we are doing. Now this though we have, but we won't get the attractor because we don't have the values of A, B and C. As you can see, they are not yet defined. They don't exist. So I have to put the values and I have to put these values so that they give me this Lorentz attractor. So I'll put this 28 can and 8 by 3. I just push this here. Now you can see the big caution. That took my 1 week. That is because if I just eliminate that float term from there, Java won't give me a float value for C. It will give me an integer. And so nothing will work. It's unlike Python, where you have that 8 by 3 and you will get something as 2.33. That is not going to happen. So you have to keep the float there. Or what you can do?
But you are defining C as a float now.
Yeah.
C as float. So
In spite I am defining C as float, it won't give me a float. You have to explicitly mention
okay.
when I am dividing two integers, one integer by another, I need the float.
Achha, if you are applying an operator, then it doesn't take it as a float.
No. What you can do instead, that is more clear, you can put 8 by 3.0. So you are saying, okay, fine, 3.0, that is a float. I need a float. That will also work. And now I can just check if I am getting some values. So I am just printing the values of x, y, and z. See here you are getting some values there. So it's fine. It's working. We are getting values. Now we have to figure out how to plot them and make that pretty big. That's it. So now we can just draw the points as those x, y, z. But where is 3D? There is no 3D yet. Okay, fine. We'll come to 3D a bit later. Let's first just make the points. I'm translating the origin to the center and giving a white stroke. Sorry guys, I didn't use the background. So there is something happening, but I can't see it very clearly. Fine. Let's scale it. This thing will scale the whole coordinate system by 5 units. Yes. So now you can see there are some attractors there about which the points are rotating. And that point just got into there and it is coming out somehow. But the thing is, can you guys tell me one thing? I am just drawing one point. There is only one point in my draw function. There is only one point. Then how am I getting all those points there? We are getting more than one point there, but we are drawing only one. What is exactly happening? This is happening because we are not refreshing our background. Our background is in the setup function. So it is only defined once in the beginning of the program. And then it is not getting redefined every time. If we do that, then you will just see one point. That point is just wiggling there, doing something. But we have to make the attractor. So for shifting in 3D, we have to just do one thing. Here, where we are defining the size, we have to say कि okay, we are switching to 3D mode. That is P3D. That is it. And now we can define our point with 3 coordinates. But nothing will change because we didn't draw anything. Now how will we draw multiple points in the screen and store all the points so that we can keep track of them? For that, we need the array. Now here we are defining the array as this. So this is the syntax for the array. We are defining an array list of something called p vector that I'll come later, and that array list is named as points, which is saying it's a new array list of p vectors. But this array list is like the list we have in Python. You don't have to define the length of the array list here. So this is a bit slower. But we can't help, we don't know how many points we will have. But there is a way to define the arrays. Can you see this thing? Can everyone read it? That's fine. So this is the way you can define an array with predefined length. So here what I did an array named any array which can only contain integers and will have a length of 5. Another array I defined which is M, which is a two-dimensional array, an array within an array, which will have a length of 4 by 1. So it is basically a matrix. But we have to predefine the lengths. That's it. These are faster because they take a single block of memory. But those that I defined before are not that fast. But we don't care. Let's see what happens. So we have our array list here. Now what we will do, we will add our points, the x, y, z that we were getting in the array list.
Why are we doing this exactly? Why are we making an array?
So that we can keep the information of the points. If we don't have an array, we can't have all the points in our cabinet settled so that we can make a graph.
So why don't we directly just shoot it to the directly show it?
Directly show what?
The points rather than storing just
I'll come to that later. Because we won't be limiting this to points. We will be making it a shape, its own shape, that I'll be doing after this. So now I stored this arrays with a wrap of something called this p vector. Now this p vector is nothing but a vector, and processing has its own ways to define a vector. The nice thing about this is it comes with its own functions, so you don't have to make it. Here I have opened it somewhere. So this is the P vector for x component, y component, z component. As you can see, you have the methods. You can see its magnitude, you can see its norm, you can add it, subtract it, multiply it, divide it, cross product कर सकते हो. You can set the magnitude, you can rotate it, you can find two angles between it. So processing made it easy for you. That's the answer. Yeah, I am putting it as a P vector there, and that's it. Now we can draw, as now we have all the parts in our array, we can draw it simultaneously with a for loop. Now the for loop that we'll be using is the print statement. Now there is an enhanced loop like you do in Python. You can, instead of picking the index of any list or array, you can directly pick the element in the array. And I am just pointing it. So let's see. Now you have the set of points drawn as it.
In my system, it isn't like recognizing array list as a class. So like,
Okay. Is anyone facing this problem? Anyone else? Social beneficial points? It's fine. What will take care of? Okay. Now come to your question. Here we are printing all the points, right? But the figure I showed you, graphs consist lines. So we have to somehow connect the points. That we will do by a very nice method in processing called this begin shape, end shape loop. This is a very nice thing to do. What we will do is we will put a begin shape here. And instead of point, we will write it as a vertex. Sorry, messed up. It is filling the whole shape that we are making. So we have to introduce the no fill. It remains line. Now it is only the outline. Now it is only the outline that we are making. Fine. So essentially I can say I'm done with it. I made it, it's fine. But we are artists. We can't leave it like that. We have to make it at least colorful. Otherwise it's like bland. And to make it colorful, I'll introduce this new thing called color mode. So yesterday's course I told you about the RGB color, where you have three components of a color: red component, green component, and blue component. And you have an alpha. So now here there is another thing that we can use for colors, that is HSV mode. HSV stands for hue, saturation and brightness. As you can see, The hue is all the colors. The saturation is from the color and how white it is, the measure of that. And the brightness is how it is distant from the black color. That is like very simple. So this is very useful to work with because now I can make it colorful very effortlessly. I'll just define, I'll just first let me make the stroke as some 100. Oh, I didn't define it. I have to define color mode as HLP, and I can do the stroke as 100 is somewhere around cyan, saturation, brightness. Let's see if it's colorful or not. It is some greenish color. Sorry about it. Like my screen color and that color is entirely different. Sorry. Anyway, now as you can see, U equal to C4. Make it U. And if U is greater than 255, I'll put U equal to 0 again. So that I keep getting colors. That will make it colorful. Why is it making it colorful? Oh, I didn't increase the hue. I have to increase the hue for every iteration of the loop. Now it should make it colorful. Yeah. This going from red to yellow, now this one green, something is happening.
So, does it reach at the starting point after some time, like doing all this thing, or it goes infinitely?
It will go infinitely because here what I have, here whenever it is crossing 255, that is the maximum range, I am again setting it to 0. So from red it will go to dark blue and then again come to red. You can speed it up or slow it down by this factor 0.1 that I am putting hue plus equal to 0.1. If I put it 0.5, it will be a lot faster. The color change will be a lot faster. Now you can see there is no red at all. And it is changing very fast.
Like, I am not actually asking about color, but like the point where this starts and does all this, will it reach the same endpoint? Like, will this complete loop end?
No. It is not closed. That thing will be bounded. Like, that is a bit scientific. So if you plot the energy diagram of this thing, and this is just, we are just plotting the differential equation and all. If you put an energy diagram of this thing, the energy diagram will be bounded. So this thing won't shoot up to infinity, but it won't close. Like there are some processes to check if some orbit that a particle is making is close or not. I'll give you some references. This is the Goldstein book. You can read it if you want. Like there they explained it for only like for central potentials, not for this sort of nonlinear things. But you will get an idea. And this thing won't be closed. Now we can see it happening, but we need a good grip on the view. We need to rotate it. We need to see it from every angle so that we can be sure that it is nice and people can appreciate it. For that, we will be using a small library in processing. that is called PZ cam. That we don't have to code everything about the rotation with mouse and all. I will show you how to install that thing and you can do that. You can go to this Java button and manage modes, and here you have this libraries option where you can search PZ cam or PZ whatever and you will get this thing, this library by Jonathan Feinberg. This thing actually, like, I'm telling you, you will love this library. This will make the rotating thing a cakewalk. It is awesome. I can shout about it for half an hour, but I won't do it. Anyway. So you can install this PZ cam thing. Now after that, what you have to do, you have to just import it like Python. And you have to define, you have to not define, you have to declare the camera. So I am naming a camera cam, which is a PZ cam object. So you will be introduced to objects during P5J, course, right? Yeah. So then you will get a better understanding of what objects are and what they are capable of. But anyway, we are just declaring the camera and we have to put it in the setup. So we are saying this cam thingy is a new PZ cam element whose position is this. I am in this 0, 0 and the z axis I can find as 500.
So, what is this camera thing which is like, how is it working? Like, is it some kind of camera inside the entire setup?
So, whenever you are going for 3D systems, you have a camera. I didn't talk about it, that's it. You have a camera that is your eye in the system where you can see everything happening. Now, this PZ cam is an efficient way to move the camera according to your mouse cursor. We can use other functions to rotate the camera that I will show you after some time. But this thing will allow to take mouse inputs and change the position of the camera accordingly. And what this thing does, remember we did this translate width by 2, height by 2 to make the center, like the origin to the center of our screen. PZ cam does it by default, so we won't be needing this. Now what we can do, we can rotate with my mouse movement and see every aspect of the thing. That we can do now. But it is sort of looking one wing of the butterfly, not the whole thing. So we have to make another one. But that's easy. That is the same thing, just flip. So we will construct the whole process all over again once more. What we will do, we will find another array list. Now this thing I will define as point 1 and this thing as point 2. Okay. What else? What else? So as we have to flip it, I am just putting a minus z so that the whole system gets flipped. And we have to draw it. This is point 1. 96, two wings of the butterfly. Now, this is actually the end of this thing, but what we can do to start it more beautifully, we can rotate the spring from the beginning. So it starts like this. I'm basically rotating the coordinate system. The x-axis and the z-axis. So that it starts like this. You then have an inherent rotation also. If you put it as an angle, you can define the angle here as a flow. And you can increment the angle at the end. So that it keeps rotating like this. And this is a bit fast, you can tweak around with that and the thing. So now you can have it rotating. So now the camera is rotating around the center. For the completion, it will be full speed. That is what I showed you before, it's the same thing. So yeah, you can tweak with it as you want. Like you can add some noise in the points so that it will be a bit wobbly or something, or whatever you want you can do with it. Like you can change the colors. You can actually find other attractors. Like here we have given these three constant values for this attractor. You can find other attractors with other values of ABC and you can plot them. So that's it for this thing. Now what you can do otherwise in processing is like, these are some things like I've made before. Like my first plan was to show you something from this, but anyway, I ended up doing that. So this is a diagram basically, or you can call it a clock. It has random ripples with the color gradient. So this thing you can make very easily with processing. So I've used something called Colding noise here. You will be learning it in P5 testing. Yeah. This is one thing. And the other thing is this is a bit slow. This is a tree. And it is completely mathematically generated. I just couldn't figure out how to make it fast, so it's not rotating very fast. But otherwise, yeah, it's a normal tree. This is a shadow of a tesseract, you can say, which is rotating in the new axis, so that it is behaving like that. Like it is sort of coming inside out. This thing also you can do, like, this is a bit complicated, but yeah. Once you are done with the object-oriented stuff, you can do that also. And this is the last thing. This is a Rubik's Cube that I made, and like this thing is actually, I'm working on it, but yeah, it can shuffles itself. What's reshuffling it back? You can rotate one side. I added other button function, but yeah, you can rotate it like with buttons and all. So that's it, guys, that I was trying to show you. I think you'll appreciate. Thank you.
Well, thank you, Ratnajit Bhaiya. Thank you everyone for coming. The good part about learning processing is this helps out a lot with hackathons. We will be having one really soon. I hope to see a couple of submissions in processing. Thank you for coming, everyone.